Wow, welcome back. A lot of things have happened since I recorded that video on alien technology. I was just at the mall. Okay, more than that happened. I was followed by some men in black. Oh, then I realized it was just me in the mirror because I always wear black. But then I walked into a store and a person literally handed me this t-shirt. Surprising. Although I had to give my credit card to be able to buy it. But after I gave my credit card, oh, I probably blew up the microphone. After I gave him my credit card, he handed me the shirt. Literally. So just don't talk to strangers. Oh, okay. So that's a recap of what happened since the last video. Mostly I've just been working on that constraint satisfaction problems from the Discrete Optimization class. So that's pretty much all I've been doing. Well, there's some interesting aspects to the problem now, so I figured I would talk about them a bit. There's 3 weeks worth of problems I guess I've solved. The first one was considered a knapsack problem, and it's a classic one if you look it up. The idea being that I encounter this all the time in role-playing games and other games online, where you have a backpack or a knapsack, and you can only carry so much stuff in it. Like Skyrim does this. You can carry, say, 100 kilograms, but everything has a different weight and different price to it. So some objects are really lightweight, but are worth a lot. So it may be worth, it's 1 kilogram, but it's worth 100 gold. It's like, okay, well, you want to stack up as many as you can. And the question is, why would you want to do that? Well, it's because of the density, the value density. If you took the price divided by the weight, you'd say, oh, it's 100. But then if you find a bunch of like lead arrows or things like that, it's like, okay, well, each of them weighs 10 kilograms and are worth 1 gold. And so gold divided by the weight is 0.1. So the idea being, well, you don't want to carry as many of those. But you don't really know when you start off. You say, oh, okay, well, I found all these arrows. Sure, I'll carry those. Then you find some trinket on the ground. You have to say, well, okay, my backpack is full. I should get rid of stuff. Well, the question then becomes, well, what if you knew in advance? You said, okay, I know everything, on the value of everything I'm going to find and the weight of everything I'm going to find. And their backpack is 100, but things are like 25 and 30 and 10 and 1. It's like, well, it doesn't always fit in exactly. So you'll put everything in that you have, and you find out you have 5 kilograms left over. It's like, well, what do? You don't have anything that fits in that 5 kilograms. You already have all the 1 kilogram gold in there. But you have some things that are like 10 kilograms. Like, well, should you get rid of stuff and put that in? Or will you have, because at the end you want to cash in and get as much money as you can, right? The idea of you carrying stuff around is what's the maximum value you can carry in that backpack. And they say it's a common problem. It happens a lot in the world. It's like you have some amount of space, amount of weight you can carry, or certain things like that. And it's like, well, you want to get the maximum value density possible. And so that was what the key to the solution for that one was. I mean, you could iterate over every possible solution. But say there was like 10,000 or a million items. And it's like, okay, well, if you want to try all the possibilities, it's not possible within the time frame of the life of the universe even. So say you had a million items you wanted to compare. It's like, well, okay, the first item you'd put in the backpack and then say, okay, I still have room left. Put the second item in, still have room left. And then you just keep trying all the way for every possible combination. Well, so every object could either be in your backpack or not in your backpack. So that gives it a binary value of 1 or 0. So that means for a million items, that'd be a million bits of information that you'd have to try. I mean, 32 bits of information is what a 32-bit computer is, and that's 4 billion. So try 4 billion possibilities. So 2 to the million is, I don't even know if there's a name for that number, but it'd be so large that it's not possible to try all those combinations. And so the idea behind this class and all the other stuff is how do you prune that down? How do you eliminate possibilities? So, I mean, you can realize that if you have a simple example is you have 100 kilograms you can carry, and you have an item that's 101, well, you're not going to carry it. So you've eliminated that option. You don't even have to bother checking 1 or 0 for everything possible. So if you had 32 items, now you only have 31 to compare. The other thing is when you get down to fewer items, and you say, okay, well, I only have 50 space left, and I have something that's 51. It's like, okay, you don't need to compare that. But how do you prune that sooner? I mean, it's still a lot of stuff. You're only cutting out 1 or 2 items. And so the solution that I used for mine, which ends up solving all the problems in milliseconds, was just calculate the density of every object that you have or is in the problem set, and then just fill the backpack starting with the highest value item or highest value density, and work your way downward until you get to the item won't fit that you have left. So if you're at 100 and you're down to 5 kilograms left, and you're about to try an item in your backpack that's larger than that, say it's like 10 kilograms, but its value density, I guess a better way of saying it. So its value density is we'll put it higher than the lowest you've ever seen so far. So say you got down to 5 kilograms left and you have nothing left you can put in your backpack, and the value of your backpack is 200 gold right now. You're like, oh, cool, 200 gold. So, but you still have some items left. So you can remove some items and put something in and try to totally fill your backpack, right? Because you still have 5 kilograms of space left. So if you remove something and put something else in, it's like, well, why would you bother? You could potentially not even bother trying that. You can remove one item and say, well, okay, with that item gone, the value density of what's left multiplied by the size. So if we remove something that was 1 in size, giving us 6 space left, but that one item took away 10 value, and the items we have left have a value density of 1. So that means that every 1 kilogram is worth 1 gold. So there's only 6 possible left. No matter how many items there are, we know that if they're sorted by density, that's the highest one possible. So removing that one item and trying to put in something else into that 6 rather than the 5 will never be better than the 200 we had previously. I could draw it out on a board, I guess, but I've given enough numbers. So the idea being you can just prune it based on that and say, okay, well, once I get to a spot where I have empty space in the backpack, even though there may not be an object that actually fits exactly, what if one of those, that object could possibly fill the entire backpack? And its density was X. Multiply X by how much space is left gives you the value. And you can say, well, that value plus whatever is in there now is never going to be greater than what's possible. Then you don't have to check any of those items. So you could have 1,000,000 items, 1,000,000,000 items, whatever. It doesn't matter. The density is never going to be greater at that point. So as long as you do a density sort, you'll always end up finding the maximum possible at the minimum amount of checks. And so that was the easiest one for that set of problems. For the second set of problems, they had graph coloring. It's used for like maps. So you have a map and you want to put a different set of colors on every country such that every country that touches doesn't have the same color. So like France and Germany wouldn't be both blue on a map. You'd have to have them different. That way you can distinguish from looking at it. And it's a fairly common thing. Use it for a lot of other things in computer science too, like register coloring, or just you have different things that you want to color at a certain time. And you want to know that they're all different. They're all not going to be used at the same time, or whenever something's connected to something else, it's not going to match. And so there's lots of ways of approaching the problem. But what I try to do when I'm looking at these kind of problems is come up with a set of functions that work on the object. Because given the first problem, I guess, was 50, and it goes up to 1,000 different nodes, so different different spots on the thing, and there could be huge number of connections between them. So you could have 1,000,000 connections between 1,000 objects, right? So you have all the ones that are connected, and it's like you're going to make sure none of the colors match. What's the minimum number of colors possible to color in that graph? So if you had a node here and here and here, it's like, and they're all connected, well, then 3 is the minimum, because this one would have to be different from this, and this one has to be different from this, and this one has to be different than this. And it's like, with 3 colors you can do that. But if this and this weren't connected, then you could do it 2 colors. It's like 1 color here, 1 color here, and this color over here would be the same. So even though the number of nodes matters somewhat, it's the number of connections. Because if you had one linear list, you could do it in 2 colors. Or there's a lot of other lists that are similar to that. The idea being, it's like, what's the minimum number of colors that you can possibly apply and make sure that they're all unique? And so there was a couple of different techniques that I had tried for that. But the one that turned out to be the most fruitful was to randomly assign all the different possible colors that I want. Say for 50, I only wanted to use 6 colors. So I'd randomly assign all the 6 colors. It's like, well, then there's going to be conflicts. Because there might be randomly assigned, so this one might be red and this might be red. It's like, okay, so it goes through and finds all the different conflicts. And that's the standard way that most people end up doing it, is they find the conflicts and then try to resolve that and say, okay, well, these 2 conflicted. Is it possible to change this one or this one such that it no longer conflicts? Is blue still available? Like, is this red one here connected to only countries that doesn't have blue in it? If true, then you can make that blue, then this one won't match, or won't interfere with any of these, and it doesn't interfere with that one anymore. And that's it. It's all resolved. And when you have thousands of those, though, I mean, it would take forever to actually find all the combinations. And so there's a lot of other stochastic or random kind of processes that one apply. And just doing that, just checking for the maximum conflicts, they call it. So find the maximum number of ones. So like this one here, maybe this red conflicts with all of them around are red. It's like, okay, well, try to change that one first and change it to one that has the minimum possible conflict. So if they're all like 6 are red and 3 are blue, it's like, well, change this one to blue if you only have 2 colors. And that kind of works. But then there's a lot of ways to resolve that. That one you have to depend on a random amount of time. The way I initially tried it was to take every country and just say, okay, well, look at all the ones that are connected to it currently and all the ones that I've colored and find the one that's missing. And if it's full, then just add 1 to the maximum number of colors. So assign a color to something, assign another color to something. When we get to the third one, and we say, okay, well, we've assigned color number 0, color number 1. We check this one here and say, well, we can't use 0, we can't use 1, so therefore I'll have to make it a 2. And then we have another one over here, and it's like we check it's 1, and it's a 2, but it doesn't have a 1 on it, or has a 0 and a 2, it doesn't have a 1, so we can assign it a 1. And if we had another one down here that's connected to all of them, we'd say, oh, it's connected to all 3, we have to make that one a 4. And the idea is that you build up your set of colors. That's the greedy algorithm that I used initially. And that one ends up getting a 7 out of 10 for all the problems on the homework. Just matching all the colors and saying, well, just every time you're about to assign a color to a node, check all the colors and just assign the minimum possible value to it. And including up the one beyond whatever the colors are there, if all the ones are taken. And that worked reasonably well, but then you can get a better solution. And the other one, like I said, the one way I did it was with the randomness, but then that didn't actually solve down to the one that was needed for 10 out of 10. So the other thing that I added was checking for holes. So if there's a way of walking through the graph to find it. So like over here, say this one here, this is red and it's surrounded by blues that are connected to it. But up to this point, we went 6 colors. So there's 4 of the colors that could possibly go into that spot. But way over here, this one's totally surrounded by colors that are all unique. But there's a pathway between it that we can swap colors and borrow one from here. Change this to something and move that color to here, move that color to here, and here, and here. And eventually get back to this one and go, oh, okay, now we've assigned a unique color to that one by borrowing one from a spot that has a hole in the color space, right? If you count all the colors that are connected to it, there's some that aren't assigned. And I call that a hole in mine, or zeros in my program. And so what I do is then I look for all the zeros within my graph, within all the connections. So I randomly assign all the colors, like I said, then find all the ones that are 0, and if this one here was 0, then it just randomly picks one of the other possible zeros and reassigns it to that. So even though it didn't need to change, by changing that potentially opens up a color for somebody else that didn't have that color, and that one could propagate itself automatically. And so by iterations through that random process, it's able to eventually move that color from here over to somewhere else that it's needed. So I think I only let it run for like 1,000 iterations of possible colors. And it found the optimal, or the solutions necessary for 10 out of 10 or better. I just would set it in advance and say, okay, well, I want it to find 6 colors on this graph. And so it would try assigning 6 and then failed and move things around. And I've just seen that there was always these holes available. So just by doing the randomness and saying, okay, reassign randomly to this, and then that would be the first step. So out of the per 1,000 iterations, the first thing it does is reassign all the zeros randomly. And then for the second part, it goes through all the colors again and says, or all the nodes again, and says, okay, minimize like I had mentioned before, minimize the number of errors. Find one that has the maximum number of errors and minimize that, so that lowers it. So overall, each step, the total number of errors is going down based on the second part, but it's also potentially propagating these holes and missing colors across the graph over a period of time. And it took about a second per color out of the 6 problems, or a second per problem to solve it that way. There's then I found online that there was people who had better solutions, slightly better, and so I let mine run a little bit longer, up to 50 seconds, and I was able to find some of the more optimal ones. But it's still not the optimal way of solving the problem. There's ways that you can do, like I was saying, you take and propagate that color through the space until you have the minimum amount necessary. So it just takes a lot more coding, and I don't know how long it would take to run, I guess. Probably a bit longer. The random search is enough for that, but it's interesting still. I want to find out better solutions. I mean, I'm trying this online class to find solutions for these kind of problems. These things are actually happening in machine learning a lot. I mean, you're going to try to find the minimum values for something, or what's the best possible solution. Right now, machine learning, they use iterative approaches and do error calculations and say, well, okay, we have a value here and we guessed here, and we take the error and say, oh, okay, we're off by this much. So what if we just move it slightly towards that and slightly towards that every time until eventually it gets to closer to the actual values we want. It doesn't necessarily, you can't necessarily do that for something like a graph coloring problem, I don't think, because usually you have to either know the answer or have an idea what you're looking for. But I don't know, it's an idea. I mean, I should try looking into that. The fourth set of problems was the standard traveling salesman problem, which is given a set of cities, which is just a set of coordinates. So, this one is 0, 0, and 1, 1, and wherever. So, and calculate the distances yourself between each of those cities. The person wants to start here, hit all the cities, and end up back here at the end. What's the minimum distance they can hit within all those? And it's another one of those that's easy to describe and easy to verify. You can say, oh yeah, this is how long it takes, but it's really hard to calculate. I mean, same thing. It would take forever to actually calculate all the possible combinations of cities. And so the same way, you have to come up with ways of pruning your tree. You say, okay, well, given a set of points, same thing. I did a random assignment of all the different possible, did a shuffle. So I assigned between 0 and, say, 51. And it picks 51 possible points. And then it shuffles them around and then says, okay, how close to the solution is that? Well, then I created a bunch of operations that keep a consistent answer. So, right, because that's a valid answer. I know I'm going from all the possible cities I've represented because I had started with all the 51. Or we can even start with 0 to 50, all the possible numbers there. Then some of the operations that don't actually affect the graph but could affect the timing, affect the distance, but so basically affect your answer, would be things like point swap. So if this city here, instead of going from this city, this city, this city, I swap these two. So now it goes from this city, this city, this city. So I just pick two random spots and swap the two, and then measure the entire distance, see what it is. And there's ways of calculating the distance shorter, right? I only change these two values. But doing that brings the value, brings it way down, so you can get shorter distances, because you just try and say, oh no, that wasn't any shorter, don't do that one. It was actually, and then I decided not to do the random, just walk every possible point in all the ones for the problem size they're using. That worked, and that reduced everything way down. Then there's a couple other things that one can do. I mean, if there's a cross, so like if we're going from this city to this city, and we're further on in the thing, it goes from this city to this city, these lines cross each other. Well, it's always shorter to do that instead, to uncross those lines, and then reverse the path between the two. So instead of going here and then this way, you go here and then this way. And that's always a shorter distance. So I have the code look for all the possible crosses continuously, and if it finds one, it just undoes that cross. And that just doing that by itself, actually, doing nothing else, starting with all the numbers between 0 and n assigned directly, just doing uncross everything, brings it down fairly close to the possible solutions. But then I did range substitution, where I find more than just like swapping points. I said, well, what if I just take this point here, say there's a point that goes, take that point there and just move it over here in the thing. So that goes and hits it here. So the point stays there. It's just the order of the points. If I move the order of the point so that it moves over somewhere else, and so that's just a move, a shift. So you take the point out of the list of your answer, move it over a bit, move it here, and this is the order of which it's going to go in. So you tell it to visit city 1, visit 2, visit city 3, visit city 5, and then way down here it's the missing cities. So it's the answer is just the list of cities in the order you're going to do it in. And so the operations are, how do you arrange the list of cities such that all the cities' numbers are still there, but the distance is minimum, right? So I'm just taking and moving operations such that I still end up with all 50 cities at the end of it. So, and just do a calculation of which one's the minimum amount of times, or minimum amount of distance. And so that one gets me 10 out of 10 on some of them, and 7 out of 10 on others, but some of the really large ones, there's one like 33,000 points. And I don't know, maybe eventually would complete, but I let it run for over an hour, and I never seemed to progress very far in any of those operations. Just doing the basic one, like just the basic swap, got me some sort of solution, but didn't even get me 7 out of 10 on the score on that. And then I found the postings of it and saw that people had much better scores than I did for some of those. So there's a lot of other possible ways of solving those. I mean, constraint satisfaction problems. So that was just the first kind of pass with creating some stuff, creating some iteration stuff for it, and some random swaps. So I don't know, was this something to try? But yeah, I'd done a lot of this kind of stuff before. I mean, it's most of the stuff is in Peter Norvig's book on modern AI. a couple chapters on that for constraint satisfaction problems. And I tried it out before. It's really fascinating stuff. I mean, the idea of taking problems that if you just wanted to try every possible solution, it's just not possible to solve it in any amount of time, no matter what, and then coming up with a solution for it. And that's kind of what machine learning is these days too, or Halite or anything like that. It's like playing a game. It's like, how do you find a solution in a reasonable amount of time? And given a set of time, can you find something that's less an optimal solution, but still good enough? That's where genetic algorithms come from, or things like that, where it just randomly tries, directedly randomly tries different possibilities, where the direction ends up, you try to direct the randomness to better and better solutions. But the idea is never will achieve an optimal solution. And never say, this is the absolute shortest distance that you can ever achieve going from city to city or with all the different graph colors. So it's never optimal, but it's much better than just random. If you just picked a random set of cities and drew all over, I mean, yeah, that could be many times larger than you would need. And then they said there's simple things, simple operations that'll reduce it by a lot. But then to get them that final last little percentage, that's when you have to actually apply real computer science techniques and apply some other more advanced things that take a lot of time to write. And I just haven't spent the time to write them yet on this for these problems. But I'm just exploring all the different ideas, different ways of trying it. And those were my thoughts on what I've been doing. That's what I've been doing for the last 4 or 5 days since the last time I uploaded a video. Oh, that and all this alien stuff, man. And then Project Blue Book, unbelievable. They created a TV show based on the TV series, or on the old TV series based on the old book, and the old project even, about aliens and technology, and alien technology. And yeah. So that's what led to the whole getting a t-shirt and everything. But yeah, I watched it. It was okay. It's worth, I can't wait to see how it progresses. It's I actually kind of enjoyed it. And as they say in the show, the aliens are among us. And maybe they have answers to these constraint satisfaction problems. And that would just save me a lot of time. Or maybe they don't, and I'll have to solve them myself. Well, guess we'll see how it goes. But anyway, those are my thoughts, and I will see you in the future. Take care. It's still recording.